other one is going to be, I don't know yet. But regardless, as soon as you begin taking that one, let's say you don't even want to do it, you could immediately give it as a 0 because one additional quiz is going to be dropped anyway. So having that third quiz in no way harms you. It only benefits you because I'll be dropping an additional one. Does that make sense? So that's the schedule for the remainder of the semester. All right. With that, let's begin. So where we left off last time, we introduced the topic of rotation. And everything can be summarized in this table right here. But one of the things that was difficult, or one of the things that we needed to do beforehand, was to go over this mathematical operation called the cross product, and that's where we got to. We actually haven't started anything with rotation just yet. The only thing that you're aware of is that whenever there is in translation, there is a rotational counterpart. Not only in terms of their basic variables, but also in the relationships as well, such as Newton's second law, kinetic energy, momentum, and so on and so forth. Now, one of the things that you're going to notice is instead of V or an A for velocity and acceleration, we have omega and alpha. Where have we seen those before? Huh?
Circular motion.
Yeah, we've seen that in circular motion. So, let's begin with an observational note. The changes from translation to rotation is reminiscent of translation to circular motion. And that is not an accident. So why is it not an accident? The answer is because consider an object rotating. So let's say we have this cylinder, and it is rotating around this axle. Instead of looking at this cylinder as a whole, let's look at just a small piece of that cylinder. So let's just focus, let's say we place a mark right here, and we'll call that 1. If this object is rotating, what kind of trajectory is that dot going to have? What is it?
Circle.
Right, circle. An object rotating, how did I make this? So, all parts of an object rotating is essentially just going under circular motion. So is in circular motion. So when an object is moving, is rotating, all the parts are just moving in a circle. Now instead of just looking at object 1, or let's say this is 2, and this is kind of in a line, let's say on a separate line, this is object 3 and 4. Let's see what other similarities these relationships have. So recall, in circular motion, the position, we gave the notation theta, which has units of radians. The velocity, we had omega, which was delta theta over delta t, or radians per second. Or we also had the acceleration, which was alpha is delta omega, delta t, which is radians per second squared. So let's say we rotated the cylinder at angle theta. Meaning, objects 1 and 2 that were right here, it's going to rotate it how much by how much? It'll be here and here. They'll have moved by what? What do we move by? The entire cylinder rotated theta. How far did this move? And how far did that move?
Theta degrees?
Yeah,
or
theta.
Or theta.
What about these two? This would have rotated what? Theta. Meaning, it's not that they're just all in circular motion, but they are in the same circular motion. They all move together. Whatever the overall object is rotating with, the circular motion that they have is identical. So, all portions have same theta. But if they have the same theta, because theta or omega is related to theta, they also have the same omega. So therefore, has same omega. But notice, alpha depends on omega. And so if they have the same omega, they also have the same alpha. And this is why the translation to rotation, we're using the same notation as the circular motion, because rotation is essentially a collection of objects moving in the same circle, or moving in the same circular motion. So yeah, that is true, and they all have the same theta as well as the omega and alpha. So in a nutshell, that's what circular motion is. It's just a collection of connected particles, but it's all, everything is moving with the same angular velocities. Now, I don't know if I told you guys, maybe it was a calculus class that I shared the story with. When I first learned this in high school, on the quiz or the exam, in my mind, I should have gotten a 0. But luckily the teacher was gracious and gave me like a 70 or something. But it was definitely the hardest section of the physics class. And now that I'm teaching it, I absolutely agree that in this semester, this is going to be the most difficult. Why do you think that's the case? Any ideas? As a way of illustration, and hopefully me telling you this will alleviate some of that difficulty, is let me ask you a simple question. Let's say you're given like a problem that you need to solve in the real world somewhere. Okay? And let's say this problem is going to take 10 steps to solve. Would you feel confident if you only knew how to do one of those steps? You'd be like, no, absolutely not. I don't know how to do majority of it. Okay, would you feel confident if you knew how to do 9 of those steps? Then would you feel confident? Who says yes? Raise your hand. And of course, you have the ability to learn and then, continue going and so on and so forth. Who says no? Raise your hand. Why not?
I feel like I'd get to the last step and then I would know what to do and it'd still be the same result.
Okay. Do you guys kind of agree? If you do, you're already duped, and this is why I think rotation is going to be hard. Because I never said it was the last step you didn't know how to do. What if it was the first step you didn't know how to do? When you begin doing the problem, you're going to be like, what is this? Let me just recall you guys back to quiz number 1. Half of you guys, maybe it was more than half of you guys, wanted to drop this class immediately. I had so many emails sent out to me like, Dr. Kim, should I continue? No. This is why I think rotation is going to be extremely difficult. I promise you, you know how to do all of the last steps because we did all of those in translational motion. What we have to do is do a few things before step 1. Unfortunately, those also tend to be the more difficult steps. And let me show you what I mean. In translational motion, you're just given mass. And then what do? You just use it. But look at what the rotational mass is. What is that? This is what makes it very, very difficult. Because when you read a problem, at least when I was back in high school, right, nobody gave me this kind of like prep talk or pep talk. When I read the problem, I was like, I should know how to do this. I just don't know where to start. And it was like that for every single problem. Because I forgot I needed to do this thing. That's it. But I just completely forgot I needed to do some work before I could even use the rotational mass. This is actually not a simple step to do, especially if you even forget that that step is even necessary. And so the hard part about the rotational aspect is not everything that comes afterward. Everything that comes afterward, out of, let's say, 10 steps, you know how to do 9 of them. It's the first step that's going to trip you up, and you're going to get the same kind of sensation that you guys got when you guys took the first quiz. Who remembers the first quiz? All right, I think pretty much everybody does because, everyone's kind of like, I guess, blindsided by it in some way, shape, or form. So let's just write this down. So what makes rotation hard? Difficult? Now, just to convince you, because a lot of people are going to say this, they're going to think, oh, it's because the math is too hard. I don't think it's the math, so I'm going to write for you guys, not the math. Because you already did a lot of the stuff in circular motion. Well, this new additional cross product thing, with a little bit of practice, it's actually not going to be too bad. So cross product, just, I would say, requires a little practice. And then you'll get the hang of it. So the math really is not too difficult. But the actual answer is need to do preliminary work. Need to do preliminary work. So we'll call, and there's 2 steps that you need to do, but I'm going to call it step 1A and 1B because they're kind of doing the same thing. This is actually step 1B. I'll start with 1B first because this is what we're trying to get to. need to get, or need to do work, to get rotational mass. Meaning, we need to use this expression. The moment of inertia is going to equal this guy. But the reason why this is step 1b and not 1a is because we need to know what these bits of pieces of information are. So this is mass of part I. What this R is this is how far from rotational point. So already, before you even can use this rotational mass, you have to do a little bit of preliminary work that gets you to understand what is the system you're even looking at. You need to be able to break it down into its essential components, as well as understand, okay, it's not only what the parts are, but where are they? And it's not only where are they, but it's where are they with respect to the rotating center. In this case, it was the axle. It was the axle. But it's not always going to be so clear cut. And this is where step 1a comes in. Step 1a, you need what is called the center of mass, or COM. The center of mass is the rotational point for a freely rotating object. This is the rotational point, or sometimes it's called the pivot point of freely rotating object. And I told you guys that this lecture is going to be super duper short. It's going to be even shorter for you guys in the calc-based class, because for them, they need to use calculus to get this. Obviously, this is not the calc-based class. So for you guys, there is a nice table in the textbook that you have to look at, depending on the different geometries. So for example, a rod, actually, hold on one second. Before that, here you can get through the table. But let's more precisely define what the center of mass is. So center of mass can be identified visually, where let's say you throw this pen and then you have a slow motion camera and you're tracking it. The center of mass is the point that is unchanging. Essentially, it's stationary. That would be the center of mass. So it's a point that is stationary when rotating. So that's the visual way. But you could also do it physically. And you could also all do this with your pens that you have right now. There's two ways. One, you just grab your pen by the tip. If you just try to move it side to side, you're going to feel that it's going to be kind of like top heavy, and it's going to try to wiggle out of your hand a little bit. If you adjust the position slightly, you're going to see it wiggle slightly less. And the exact point where the center of mass is when you try to wiggle it, it's not, or when you try to move it side to side, is not going to wiggle whatsoever. That's how you know that you found the center of mass. Another way to do it is just, use your finger and balance it. Alright, that would be the center of mass for me, for my pen. But we don't care about visually or physically, we care more about mathematically, but this is how, when that table comes in. So mathematically, for this, you need to look at the table. Different geometries will have different center of masses. For example, let's say we have a rod like this. Where do you expect the center of mass to be if it's uniform? Right in the center. And so if this was x direction and this was 0, so then at what x position, and it had a length of L, at what x position would the center of mass be? Will be at L over 2. That's what constitutes the center. If this was a 0 point on the x-axis, the center of mass would be occurring at a halfway point, which is L over 2. So before you even do the problem, before you do anything about rotational motion or anything, you need to understand what shape your object has, because that's going to determine what the center of mass is. Once you only have the center of mass, then you can calculate your moment of inertia using that expression. So then can compute I. Now here's the thing, you're not always going to need the center of mass. You only need it if it's freely rotating. However, not everything rotates around the center of mass, because instead of having the cylinder have the axle right around the center, you can have your axle all the way up here, at which point it's going to be rotating not around the center but over here. And so you can actually force different objects to rotate wherever you wish. But then I was equal to this expression. So let's list the steps. One is to get we'll call it pivot point because it's shorter than rotation point. Once you get the pivot point, then and only then can you actually get the moment of inertia I. And let's do that as an example. let's look at what is called a rotating widget. So let's say a widget is made up of 3 different, let's say, blocks, and they are all connected by massless connectors. And we are forcing the object to rotate right there. We put we drill it, we put a stake in it, and it's going to be rotating at this block. Let's say this one weighs 10 grams, this one weighs 20 grams, and this one weighs 15 grams. And I also give you the dimensions that this is 3 centimeters and this is 5 centimeters. And the question I want to answer is, at what point, or at what omega, does the widget have 50 millijoules? So this widget is going to be beginning to rotate, and we just want to know at which angular velocity will the system have 50 millijoules? Well, let's make sure we're understanding the problem correctly. Millijoules is a unit of what? Huh? Yeah, millijoules is a unit of energy. So essentially, what this problem is asking for is something regarding the kinetic energy, the rotational kinetic energy. Who remembers a kinetic rotational energy? What is it equal to? Translational one was 1/2 mv squared. And the rotational one would be 1/2. Yeah, instead of mass, it's I. And instead of V, it is what? Yeah, omega squared. Meaning omega is equal to 2 times the rotational kinetic energy over I square root. Well, do we know kinetic, the rotational kinetic energy? Yep, that is what 50 millijoules is, so we do know that. But we do not know the moment of inertia I. However, we do have enough information to get the moment of inertia I. Which is equal to the sum of mi/ri squared. And in our example, so this is just a sum of all the different portions we have. How many portions do we have? Or how many parts? We would have 3. So this is going to be m1 r1 squared plus m2 r2 squared plus m3 r3 squared. And let's say this is 1, this is 2, and that is 3. So we want m1 r1 squared. m1 is, we'll convert it to SI units, so 0.01 kilograms. What would r1 be? What would r1 be? 0, yes. Remember, r1, we need to be precise about what that is. right, this is part of the, you gotta think about what's going on. R1 is how far is it from the pivot point? And in this case, R1 is the pivot point. So it is 0. Plus M2 is going to be 0.02 kilograms. What is R2? 5 centimeters, which is 0.05 meters squared. Plus M3 is 15 grams, or 0.015 kilograms. Times R3 is 3 centimeters, or 0.03 meters squared. I do not have the, oh, I do have this number written down. This is 6.35 times 10 to the negative 5th kilogram meter squared. Yeah.
Do we have to convert it to kilograms?
Yes, you need it to get to SI units, or you're not going to get the unit of joules. Yes. And so here, it's only understanding or remembering you needed the moment of inertia I, that you knew what to do with the various pieces of information. Because normally, if you still were thinking from the translational state of mind, you're going to be like, oh, you have masses, and then what? And that's the hard part. There is a step 1 that you actually have to do before you do anything else, and that's right here. You have to get the moment of inertia. And once you do that, you can plug this in. You get omega is equal to the square root of 2 times 0.05 joules divided by 6.35 times 10 to the negative 5th kilogram meter square rooted. And I do not have the number that this is due. Yeah.
Why is it 0.05 joules? Wouldn't it be negative 5? Or where did it come from?
50 millijoules.
Oh, right.
Now, just like the center of mass, the moment of inertia is also given for simple geometries. I is given for simple geometries. So you don't always have to do the full in-depth analysis. In this case, when you had a fixed number of objects, calculating the moment of inertia I is totally feasible. However, what if you had a rectangular disk, a plate, so on and so forth? All right, those get a little bit hairier. However, it's all given in a table. So in table in textbook. Now, I am forgetting if I have it in your handbooks. If it's not, I'll be providing that information to you. You don't have to memorize these tables. You will have access to them. Well, yeah, this is where I got to. So we will call it a day here.